Hello everyone. Today, we will study the composition and performance evaluation metrics of inking devices. The role of an inking devices is to apply a thin, uniform layer of ink to the printing plate in a timely, stable, and controlled manner. The inking devices of an offset press generally consists of three parts: ink supply unit, ink distribution unit, ink form rollers. First, ink supply part. As shown in part 1 of the figure, the ink supply part consists of an ink fountain, an ink fountain roller 4, and an ink transfer roller 5. Its main functions are to store ink and transfer it to the ink distributing part. The ink fountain roller 4 transfers ink to the ink transfer roller 5 during rotation. The ink transfer roller 5 reciprocates periodically, passing the ink from the ink fountain roller 4 to the first ink distributing roller 1 in the ink distributing part. Second, ink distributing part. As shown in part 2 of the figure, the ink distributing part mainly consists of three types of rollers: ink distributing rollers 1, 2, 3, ink leveling rollers 6, 8, and ink weighting rollers 7, 9. Its main function is to transform the ink transferred from the ink fountain roller into a thin and uniform ink film. Gears are installed on the journal of one side of the ink distributing roller. Its rotational power is obtained from the gear at the end of the plate cylinder through an intermediate gear. The rotational power of the ink leveling roller comes from the frictional force between it and the adjacent ink distributing roller. The ink is spread evenly in the circumferential direction of the ink rollers through the counter rotation of the ink distributing rollers and ink leveling rollers. Meanwhile, the ink distributing roller moves axially back and forth through a crank connecting rod or cam mechanism. Therefore, during the counter rotation, there is also axial relative sliding between the ink distributing rollers and ink leveling rollers, spreading the ink evenly in the axial direction of the ink rollers. Third, ink applying part. As shown in part 3 of the figure, the ink applying part consists of a set of ink applying rollers 10, 11. This set of ink applying rollers takes an appropriate amount of uniform ink from the ink distributing roller 3 and transfers it to the plate, playing a role in coating an ink film on the plate. In some models, the ink applying rollers can also move axially to a small extent. Performance indicators of the inking device. The performance of the inking device includes static performance and dynamic performance. The main static performance indicators for evaluating its advantages and disadvantages include the ink distributing coefficient, ink applying coefficient, ink storage coefficient, number of ink transfer lines, and ink applying rate. The main dynamic performance indicators are the response time, stabilization time, and consistency of ink film thickness during the ink transfer process. First, static performance indicators. 1. Ink distributing coefficient. The ink distributing coefficient reflects the ability of the ink distributing part of the inking device to quickly spread the relatively concentrated ink transferred from the ink fountain. It is calculated as the ratio of the sum of the areas of the ink rollers in the ink distributing part to the area of the plate. K sub y equals pi times L times the summation of d sub y divided by f sub p, equation 6-1, where L, length of the ink roller, summation d sub y, sum of the diameters of all ink leveling rollers, ink distributing rollers, and ink weighting rollers in the ink distributing part, f sub p, area of the plate. The larger the ink distributing coefficient, the better the ink distributing performance. It can be seen from the above formula that the ink distributing coefficient can be increased by increasing the number of ink rollers or the diameter of the ink rollers to obtain good ink distributing performance. The value is generally between 3 and 6. 2. Ink applying coefficient. The ink applying coefficient reflects The uniformity of the ink transferred to the plate by the ink applying rollers. It is calculated as the ratio of the sum of the areas of all ink applying rollers to the area of the plate. K sub z equals pi times L times the summation of d sub z divided by f sub p, equation 6-2. Where summation d sub z, sum of the diameters of all ink applying rollers. The larger the value of the ink applying coefficient, the better the uniformity of ink application. It can be seen from this formula that the ink applying coefficient can be increased by increasing the number of ink applying rollers or the diameter of the ink applying rollers. However, if the ink applying coefficient is too large, the structural size of the machine will also be too large. Generally, for sheet-fed offset presses, K sub z is in the range of 1.0 to 1.5. And for web-fed offset presses, it is in the range of 0.65 to 1.0. 3. Ink storage coefficient. The ink storage coefficient reflects the ink storage capacity of the surface of the ink rollers in the inking device, and the ability to automatically adjust the uniformity of the ink film. It is calculated as the ratio of the total area of the ink rollers in the ink distributing part and the ink applying part to the area of the plate, that is, K sub c equals pi times L times the sum of d sub y plus the sum of d sub z, all divided by f sub p. And it is equal to K sub y plus K sub z 6-3. Where summation d sub y, sum of the diameters of all ink leveling rollers, ink distributing rollers, and ink weighting rollers in the ink distributing part. Summation d sub z, sum of the diameters of all ink applying rollers. The larger the value of the ink storage coefficient, the greater the ink storage capacity on the surface of the ink rollers. Therefore, the ratio of the ink consumption for printing one printed matter to the ink storage capacity on the ink rollers is smaller, and the performance of automatically adjusting the ink amount is better, which can ensure that the ink color of a batch of printed matters is consistent. However, if the value is too large, problems such as a longer dynamic response time and a slower inking speed will occur. 4. Number of ink transfer lines n. When ink is transferred in the ink distributing part, the number of contact lines of the ink rollers is called the number of ink transfer lines, denoted as n. The larger the number of ink transfer lines n, the more times the ink is rolled and pressed by counter rotation. The finer the ink particles, and the easier it is to spread the ink evenly. The number of ink transfer lines can be increased by increasing the number of ink rollers. And at the same time, the ink distributing coefficient is also increased. 5. Ink applying rate V. The ratio of the ink amount supplied to the plate by a certain ink applying roller to the total ink amount supplied to the plate by all ink applying rollers is called the ink applying rate of this ink applying roller, denoted as V. The size of the ink applying rate of each ink applying roller directly affects the uniformity of the ink film on the plate. Therefore, the ink applying rate is a very crucial indicator. It is not only related to the number and arrangement of the ink rollers in the inking system, but also related to the material of the ink rollers, the distribution of images and texts on the plate, etc. In the direction of plate rotation, the ink applying rate generally takes the form of more in the front and less in the back. Usually, the first two ink applying rollers apply more than 80% of the ink amount to the plate to provide rich and uniform ink to the plate. The last two ink applying rollers apply less than 20% of the ink amount, playing a role in compensation, further ink leveling, and ink collecting. There are generally 3 to 6 ink applying rollers, and 4 is the most common number. Second, dynamic performance indicators. Static performance indicators and dynamic performance indicators are often contradictory. For example, the larger the number of ink transfer lines, It means that there are more ink rollers in the ink distributing part of the system. The ink is divided more times, and the ink is easier to spread evenly. But it also means that it takes longer for the ink to reach a stable state. 1. System response time, T sub A. It refers to the time elapsed from the change of the inking amount at the input end of the inking system to the start of the change in the ink film thickness on the substrate at the output end of the system. 2. System stabilization time, T sub R. It refers to the time elapsed for the inking system to transition from one stable ink balance state to another new stable ink balance state. 3. Consistency of ink film thickness. It refers to the degree of closeness between the ink film thickness on the substrate and the target ink film thickness, expressed by the standard deviation between the two. The smaller the standard deviation, the smaller the deviation value between the ink film thickness and the target ink film thickness, and the better the consistency. This concludes today's lesson.